What if the universe you're living in is only pretending to be stable, not metaphorically, physically? Imagine a room where the walls look solid, but one thin patch is actually a shortcut to a deeper energy state. Now imagine that patch could open anywhere, at any time, and when it does, the laws of what happens next change everywhere inside an expanding bubble. That's the unsettling idea behind false vacuum decay. Here's the misconception to kill first. Many people hear vacuum and think nothingness. But in quantum physics, a vacuum is more like the lowest energy state of a field, an organized backdrop that still has properties, energy, and rules. So, if that state is only metastable false rather than truly lowest, then decay isn't science fiction. It's a predicted quantum process. The open loop is simple. If decay is possible, what determines the vacuum lifetime, and what does decay even look like in spacetime? Before modern particle physics, the prevailing intuition was that the vacuum should be the absolute minimum of energy. End of story. But the Higgs field already hints otherwise. Its potential energy landscape can have multiple valleys, and the standard model parameters suggest our current vacuum might sit in a long-lived valley, rather than the deepest one. Cosmology adds fuel. In the early universe, temperatures and quantum fluctuations constantly kicked fields around, and as the universe cooled, fields could get trapped in a local minimum. That's the before state, a stable-looking configuration that's actually metastable, like a ball perched on a hillside. So how does false vacuum decay work? Start with the energy landscape. Think of a hill with a bowl-shaped valley that isn't the bottom. Classically, the ball would need enough energy to climb out over the hill to reach the lower bowl. But quantum mechanics allows a different move. Tunneling. Even without the required energy, there's a non-newer probability that the system's field configuration can fluctuate into a bubble of the true vacuum, an interior region where the field has rolled down while the exterior remains in the false vacuum. The bubble isn't just a random blob, it has a critical size. Below that size, surface tension from the boundary between vacuum makes the bubble shrink back. Above it, the energy balance flips. The true vacuum interior is energetically favored, so the bubble expands. In spacetime terms, the dominant quantum transition resembles a Euclidean bounce, a particular field configuration that minimizes the action, encoding how tunneling beats the barrier. When the bubble forms, entropy doesn't merely vanish, it rearranges. The process releases energy as the field drops to a lower state, and the surrounding region experiences a rapid, out-of-equilibrium conversion of vacuum energy into particles and radiation. That's the entropy burst. It happens because the new vacuum has a different vacuum energy density, and that energy feeds modes that thermalize or produce a hot plasma. Here's the key result for lifetimes. The decay rate per unit volume depends exponentially on the bounce action. Even if tunneling is wildly improbable, per microscopic patch, the universe is enormous. The vacuum lifetime is thus a race between suppression and volume growth. Total risk grows roughly as decay rate times space-time volume. That's why two vacua with slightly different barrier heights can have lifetimes that differ by unimaginable factors. In the standard model context, estimates suggest metastability could be extraordinarily long enough that we shouldn't expect a decay event in any practical time frame, but not guaranteed forever. Now zoom out. Why should we care beyond a grim existential thought experiment? Because vacuum stability directly shapes cosmology and predictions for the early universe. Inflation, phase transitions, and the origin of matter all depend on the structure of field potentials. If our vacuum is metastable, the history of how the universe settled into its current state matters. Did it get trapped after inflation, or did it roll into place later? Vacuum decay also constrains new physics. If the Higgs potential is metastable, extensions of the standard model can change the high-energy behavior, lifting the barrier, stabilizing the vacuum, or altering the bounce action. That means experimental hints in particle physics can translate into statements about cosmic longevity. There's also a deeper conceptual implication: what stability means in quantum field theory. Stability here is not absolute, it's statistical. The vacuum isn't a permanent foundation, it's a conditional arrangement whose lifetime is encoded in quantum amplitudes and entropy releasing dynamics. That reframes how we interpret laws of nature. The laws we experience emerge from the vacuum configuration of fields. If the vacuum can transition, then the backdrop is part of the dynamical system, not a fixed stage. So where does that leave us? We began with the unsettling idea that the universe might sit in a false vacuum, a metastable state of quantum fields. Then we unpacked the mechanism. The field can tunnel into a bubble of true vacuum. The bubble grows only if it exceeds a critical size, and when it expands, it converts vacuum energy into real particles and entropy bursts in the aftermath. Finally, we connected the mathematics to lifetimes. Decay rates are exponentially sensitive to the bounce action, and the universe's size turns those tiny probabilities into meaningful risks over spacetime. The mic drop is this: the vacuum isn't just empty, it's a metastable phase of reality with a clock built into quantum tunneling. If you want more deep physics explained like this, subscribe for the next one.